So today in this lecture we are going to discuss a topic from unit 4, that is synchronous motor. This topic comes under the subject fundamentals of electrical engineering. This subjects float in both the semester. So code is BW101 and 201. So let's start with this lecture. So contents of this today's lecture is introduction to synchronous motor, that we will discuss what are the synchronous motor. Then we will discuss the construction of synchronous motor, then the principle of operation, then methods of starting, as these motors are not self-starting. So there are different methods to start the synchronous motors. So we will discuss the methods of starting and then the applications of these synchronous motor. So let's start with the introduction part. So what are the synchronous motor? So the definition of synchronous motor states that it is an AC motor in which at steady state rotation of the shaft is in sync with the frequency of applied current. So synchronous motor, they works on AC motor, but here the total number of rotations made by shaft is equal to the integer part of frequency of the applied current. So the synchronous motor doesn't rely on induction current for working. In these motor, unlike induction motor, multiphase AC electromagnets are present on the stator, which produce a rotating magnetic field. Here rotor is of a permanent magnet which gets synced with the rotating magnetic field and rotates in synchronous to the frequency of current applied to it. So this is where the term synchronous motors come from, because here the rotor is also rotating at a synchronous speed. So these types of motors are called synchronous motor. Whereas in case of three-phase induction motor, the rotor does not rotate at a synchronous speed. The speed at which it rotates is called asynchronous speed or subsynchronous speed. So the three-phase synchronous motors are not called synchronous motor, but they are called asynchronous motor, because there the rotor is not rotating at a synchronous speed. Whereas in synchronous motor, the name comes as a synchronous motor because here the rotor is rotating at a synchronous speed. So this is where the term synchronous motor comes from, as the speed of rotor of the motor is same as the rotating magnetic field, and we know the speed of the rotating magnetic field is called synchronous speed, and it is a fixed speed motor because it has only one speed, which is synchronous speed, and this speed is synchronized with the supply frequency, and the synchronous speed is given by 120 F by P, where this F is the supply frequency and P is the number of pole. So the construction, if we coming to the construction part of the synchronous motor, the construction of synchronous motor, so basically it has a salient pole rotor which can be seen in the figure. So just like any other motor, is consist of stator and rotor. So it has two parts. We know that the stationary part is called stator and the rotatory part is called the rotor. So it has a two part, stator and rotor. So the stator core is constructed with a thin silicon laminations and insulated by surface coating, and we know why we use the thin sheets, laminated sheets, to reduce or to minimize the eddy current and hysteresis losses, right? So the stator has axial slots inside in which three-phase stator winding is placed. The stator is wound with a three-phase winding for specific number of poles equal to the rotor poles. So here we can see that this is a our stator and this is a rotor which is of a salient pole type of rotor. Here all the poles are projected, right? So the rotor is a synchronous motor, is mostly of salient pole type. DC supply is given to the rotor windings here via slip rings, and the direct current excites the rotor winding and creates electromagnetic poles. So because of in this winding, when the DC supply is given, then the poles will be created, right? They are the electromagnets. The poles will be created, alternate poles will be created. So in some cases, permanent magnet can also be used here in place of electromagnetic poles. So now coming to the working principle of synchronous motor. So synchronous motor, it works on the principle of magnetic locking. So now what is this magnetic locking? So when two unlike poles are brought near each other, and if the magnets are strong, there exists a tremendous force of attraction, right? So in the figure we can see, if this is a north pole and this is a south pole, and if they are placed nearby, so there will be a tremendous force of attraction between these two. So if we rotate this magnet, so this magnet will also get rotated with this magnet 1, right? So if this is a magnet number 1 and this is a magnet 2, and here we have a north pole and here we have a south pole, so we know that in magnets, unlike poles attract each other. So if there is a attraction between these two poles, and if we move this magnet, so this magnet will also be get moved in the same direction in which this magnet is moving. So in such condition, the two magnets are said to be magnetically locked. If now one of the two magnet is rotated, the other also rotates in the same direction with the same speed due to force of attraction, and this is magnetic locking condition, and this is called the magnetic locking. These two magnets are locked here. So this same principle is used in the synchronous motor. So to have magnetic locking condition, there must exist two unlike poles, and magnetic axis of two must be both very close to each other, right? So this should be the condition for the magnetic locking. Now how this will work in the synchronous motor. So for this, let us consider a three-phase synchronous motor whose stator is wound for two poles. So here we have taken example that the stator is wound only for the two poles, right? So the two magnetic fields are produced in the synchronous motor by exciting both the windings stator and rotor with the three phases supply and DC supply respectively. We know that the rotor will get excited by the DC supply and the stator will get excited by the three-phase supply. So when the three-phase winding is excited by a three-phase AC supply, then the flux produced by the three-phase winding is of rotating type. So now here, when the three-phase supply is given to the stator, so we know that by giving three-phase supply to the stator, a field will be generated which is rotating in the nature. So rotating magnetic field will get developed in the stator. So such a magnetic flux rotates in speed at a called synchronous speed. We know that the speed of rotating magnetic field is called synchronous speed. So now the field which is getting generated in the stator of the synchronous motor is rotating at a synchronous speed, and the magnetic field is called rotating magnetic field. In this case, as the stator is wound for say 2 poles with 50 Hz supply, the speed of the rotating magnetic field will be 3000 rpm. So the speed of the rotating magnetic field will be 3000 rpm. So how we can calculate? We know that ns is equal to 120 f by p, right? So this will be 120, f is given 50 and p is for 2 poles. So here we will get 3000 rpm. So the speed of this rotating magnetic field will be 3000 rpm for the case we have considered here, right? So this effect is similar to the physical rotation of 2 poles with a speed of ns rpm. So this can be compared with a similar physical rotation of the 2 pole with a speed of ns rpm. So now for simplicity of understanding, let us assume that stator poles are N1 and S1 which are rotating at a speed of ns. So now here we have considered that there are 2 poles in the stator, that is N1 and S1, and which are rotating at a speed of ns. Now the direction of rotation of rotating magnetic field, now say it is clockwise. So these 2 poles are rotating in clockwise direction with a synchronous speed, right? So when the field winding of rotor is excited by DC supply, it also produces 2 pole. So assuming the rotor construction is of also 2 pole. So here we are considering that rotor is also having a 2 poles. So now when the rotor is excited by the DC supply, then it will produce a 2 pole. So assuming rotor construction is of 2 poles, salient type, let these pole be N2 and S2. Now these 2 poles are N2 and S2. So for stator we are considering N1 and S1, and for rotor we are considering N2 and S2. So now one magnet is rotating at ns having pole N1 and S1, and while second magnet is stationary having pole N2 and S2. If somehow the unlike poles N1 and S2 or S1 and N2 are brought near each other, the magnetic locking may get established between stator and rotor pole. Now suppose this is your stator, and stator we have two poles. This is now N1 and this is your S1 pole. So, and then we have a rotor. This is S2 and this is N2, right? So, if somehow this S2, one second, if somehow this S2 gets locked with N1 and this N2 gets locked with S1, so we know that this N1 and S1, they are rotating in a clockwise direction with synchronous speed. So obviously if these two poles are getting locked with each other, so this rotor will also rotate with the synchronous speed, right? So that's why they are called synchronous motor. So now, as the stator poles are rotating due to magnetic locking, rotor will also rotate in the same direction as that of a stator pole, that is in the direction of rotating magnetic field with the same speed, that is ns, which is synchronous speed. So hence, synchronous motor rotates at one and only one speed, and that is called the synchronous speed. So, but this all depend on the existence of magnetic locking between the stator and the rotor poles. But practically it is not possible for stator pole to pull the rotor pole from stationary position into magnetic locking condition. Hence, the synchronous motors are not self-starting. They work on the same principle, but when the motor starts, this is practically not possible that rotor magnets get locked with the stator magnets, right? Because the rotor is stationary and it is not possible to for the magnetic locking when the motor is getting started. So now these synchronous motors are not self-starting motors. So now why this magnetic locking does not get established at the starting phase? Now consider the rotating magnetic field is equivalent to the physical rotation of two stator pole N1 and S1. Consider an instant when two poles are at such a position where the stator magnetic axis is vertical. So here now consider, so these are the stator pole, right? So this is N1 and this is S1. So they are at the vertical position, and at this instant rotor poles are arbitrarily positioned. So arbitrarily positioned, or suppose this is the rotor, which is of course a two pole rotor. So here it is N2 and here it is S2. Right? So at this instant the rotor is stationary, right? And unlike poles will try to attract each other, and due to this rotor will subjected to an instantaneous torque in the anti-clockwise direction, as you can see in this figure. So in this figure, one second. So in this figure, now you can see that this N2 will get attracted to this S1 and this S2 will get attracted to this N1, right? So here the anti-clockwise torque will be acting on this rotor, right? Now the stator poles are rotating very fast, right? They are rotating at a synchronous speed. So due to inertia, before rotor hardly rotates in the direction of anti-clockwise torque to which it is subjected, the stator poles changes their position. Consider an instant half a period later where stator poles are exactly reversed, but due to inertia rotor is unable to rotate from its initial position, and this can be seen in this figure, right? So now here we have seen that the anti-clockwise torque is acting on this rotor, but we know that stator poles are rotating at a synchronous speed. So before it can rotate, the rotor can rotate, the position of these poles will get changed. Now here we have a S1 and now here we have N1, right? Now this N will will get will move toward this S1 and this S2 will move towards this N1, right. So, at this instant, due to unlike poles trying to attract each other, the rotor will subjected to torque in a clockwise direction. So, previously we here the anti-clockwise torque is acting, and now here the clockwise torque will be acting. So, this will tend to rotate the rotor in a direction rotating magnetic field, but before this happens, stator poles again changes their position, reversing the direction of torque exerted on the rotor. As a result, average torque exerted on the rotor is 0, right, and hence the synchronous motor is not self-starting. So, the magnetic locking will not get established when the motor is getting started, right. So, now there are different starting methods of synchronous motor. So, we can use different methods like by using pony motor. So, by using a small pony motor like a small induction motor, we can start the synchronous motor. This small induction motor is coupled to the rotor of the synchronous motor. So, this small induction motor, this is coupled with the rotor of the synchronous motor, and the function of this induction motor is to bring the rotor to the the function of this induction motor is to bring the rotor of the synchronous motor to the synchronous speed, right. So, once the rotor attains the synchronous speed, or we can say the magnetic locking is established, the pony motor is discoupled from the rotor. The synchronous motor continues to rotate at synchronous speed by supplying DC excitation to the rotor through the slip rings. Now, the next is by using small DC machine. So, by using a small DC machine, so many times large synchronous motors are provided with a coupled DC machine. So, this machine is used as a DC motor to rotate the synchronous motor at a synchronous speed. Then the excitation to the rotor is provided. Now, once the motor starts running at a synchronous motor, the same DC machine acts as a DC generator called exciter. The field of the synchronous motor is then excited by this exciter itself. Now, so because as now the rotor is locked with the stator magnetic field, so now no more DC motor is required. So, the same DC machine now can be used as a DC generator for providing the excitation to the rotor field winding, right. Then by using damper winding. So, the damper winding. So, when a 3-phase supply is given to the synchronous motor, it fails to start, right, we know that. So, in order to make it start, copper bars circuited at both ends, similar to the squirrel cage rotor of an induction motor. So, we have seen the squirrel cage rotor of the 3-phase induction motor. So, in a squirrel cage 3-phase induction motor, instead of wiring, what we use? We use the instead of wiring, we use copper bars, right? And all these copper bars, they are placed on the rotor and they are short circuited by using the end rings, right? So, a similar structure is created here also, and they are placed on the rotor, and these bars or winding are known as damper winding, and here they are called the damper winding. So, basically we are starting this synchronous motor as a 3-phase squirrel cage motor, right. So, first we are operating this machine as a 3-phase squirrel cage motor, and once the rotor gets locked with the stator, like rotor, the magnetic locking is established, the damper winding will automatically be out from the circuit. So, now when the supply is given to the field winding setups, a rotating magnetic field, due to damper winding use, the rotor starts rotating as an induction motor, right. So, we know that induction motors do not start as with a synchronous speed. So, they are less than the synchronous speed at starting. So, once DC excitation is given to the field winding and the motor is then pulled to the synchronism, right, and the damper winding will be out from the circuit, because now the rotor is rotating at a synchronous speed. So, when rotor will start running at a synchronous speed, there will be no induced EMF in the damper winding, no current. So, damper winding will automatically be out from the circuit. Then, the damper winding is used to start the motor and hence can be used for starting purposes only, because once the rotor rotates at synchronous speed, the relative motion between the damper winding and the rotating magnetic field will be equal, and hence induced EMF, as I told you, and the current will be 0. The damper winding will be out from the circuit. Now, they can be started as a slip ring induction motor, or we can say that first we are running this synchronous motor as a slip ring induction motor. So, in this method, an external rheostat is connected to the rotor through slip rings. Here ends of the damper winding are brought to the motor and connected either in star or delta. The rheostat is connected in series with the rotor, and at a starting high resistance is connected with the rotor to limit the current drawn by the motor. As the motor starts as a slip ring induction motor at starting, it draws large current. So, when motor picks up its speed, resistance is gradually cut off from the rotor circuit. As the speed reaches near the synchronous speed, DC excitation is given to the rotor and it is pulled to the synchronism, right. So, these are the different methods of starting the synchronous motor, and these are the applications of synchronous motor. So, the first, they can be used for the power factor correction. Overexcited synchronous motor works as a synchronous condenser and are used for the improvement of power factor for industrial loads having lagging power factor. Then, for the constant speed application, synchronous motor providing constant speed at high efficiency. So, they can be used for constant speed applications such as centrifugal pumps, blowers, line shaft, motor generator set, synchronous clocks, air compressor, textile mill, paper mill, etc. They can also be used for improving voltage regulation for long transmission lines. A synchronous motor with a field regulator can be used to control the voltage at the end of long transmission lines by varying its excitation. Then, for the frequency changer, a synchronous motor can be used to drive another alternator to generate supply at different frequencies due to its constant speed nature. In this case, it is called frequency changer. So, these are the different applications of synchronous motor, and these are the references which I have referred for this lecture. Thank you. Jai Hind.